Hi guys, it is Mr. Dave with the RayKitty Creation Workshop, and you are watching the RayKitty Science Project. I want to give a big shout out as many times as I can to the wonderful folks over here at Studio 519. You guys are awesome. Thank you so much. From like cameras, finding what I'm doing, to making sound work and stuff like that. I really appreciate you guys, just so we have that on tape. So I really appreciate you guys. Well, today we are going to be doing some science that is kind of just falls under what's called discrepant events. Okay, now discrepant events just mean something is going to happen in a way that you didn't quite think it was going to happen. Okay, magic tricks are discrepant events, but those are tricks. These are actually all science, and it's science that goes in a way that maybe you wouldn't expect. And we have some very small things that we'll be doing, and then we have some very large things that we'll be doing. Most of these you can do at home. If you get into your RayKitty little science kit there that you're putting together, you will want to have some pennies. We've used pennies on the show before. The pennies I have here, one is very dirty, one is very clean. That's not like integral, that doesn't have to be as far as your little experiment, but it is one way that you can kind of vary those experiments. I have here a pipette. You can use a dropper. If you have a little eyedropper in, with your medical supplies or something like that, make sure kids, if you are getting into something like that, mom and dad knows, they make sure that it is clean and sterile, there's nothing in it, but a little eyedropper will work. You can also, for this one, it takes a little bit more time, but you can use a straw. If you plug the end of a straw, you can hold the water in there and just let it out drop by drop. But there's a lot of different ways, but what you're really using this for is just making little bitty droplets. Okay, so a pipette and some pennies will be for one of them. One of the other ones we're doing, I have some balloons, if you want to get some balloons. There are a lot of different ways you can do this particular one. I just grabbed a piece of tubing, okay? And all this is going to be is it's going to be a junction between two balloons. So there's a lot of different ways you can do that, but a tubing is kind of visible. You'll be able to, see a little bit in there. That's not necessary, but it's really just a junction between two balloons. So balloons, as I mentioned. Now those are kind of the ones that you can do at home. I have some other things that I'll be doing that if you, were to kind of look around on the wonderful interwebs, you would be able to find these things, but they're a little less common and they're not really household devices, okay? So when we're working, we're gonna start with some very easy, small stuff, and we are going to be working with our pennies, okay? Now this one here is a great one if you have young students. This one here I have done with high school students. High school students, of course, it automatically turns into a competition, and as it should. But the question that we would have in our discrepant event would be, how many drops can you fit on a penny? And that's it. And so if you are working with students, they can write down hypotheses, they can write down ideas on how they're doing that. This is a great one for a science fair because they can actually demonstrate that in person. And then we could look at using different coins, okay? I have a quarter here. I have pennies that have got a lot of oxidation on there that we've used for some previous experiments. But the variable that you could use there is the size of the coin, okay? Now today we're just going to do our penny, okay? We're going to do a nice, clean, shiny penny. You can see how it works. You at home, you can work with some of these other coins and kind of compete with your family members. If you're doing this in a school setting, you can have different coins so they have different variables. Again, if you're doing a science fair, this is a fun one. Now this is an experiment in surface tension, okay? So I have water here. Surface tension is when you have a liquid, okay? Is water wet? That was a question that I was debating with my daughter and her cousin Nicholas just yesterday. Water's not wet. And I can get into that science later. But we are going to make a penny wet, okay? Now first, what you're going to want to do with your penny before you're doing the experiment, unless you're using it as a variable, is to really wipe that penny off, okay? So I'm going to clean that penny up. and we're going to be doing some like real kind of close-up stuff on this little penny right here. And what we're going to be doing is I filled my pipette with water, and the question is, how many droplets can you fit on that penny? Okay, now a penny's not very big. If you said a droplet was about that size, right? That's 3 droplets in my hand there. Then you'd say, okay, well, we should be able to fit about 3 or 4 droplets on that penny. Now we're going to look at surface tension. So when we're doing this, you want to make sure that your students or yourself are really trying to make those droplets the same size. Okay, now I'm going to do some fairly large droplets just for the sake of time, but I have 2 droplets on there. The most common guess that I get when I'm beginning this experiment is 10. Students assume that you can fit 10 droplets, okay? I believe I'm at 5 there, 6, 7, 8, 9, 10, okay? I have 10 droplets on this penny right now, and as you can see, it hasn't even really spread over the entire penny. Okay, so what we're going to do is we're going to continue adding those droplets. And like I said, I'm doing kind of large droplets just for the sake of time for on the TV here. But when you're doing it at home, you'd want to do some small droplets. Unless I lost count, that should be 17, 18, 19, 20. Now we're going to look into the science of things. And when we're looking at that penny, instead of that penny just that water laying nice and flat on that penny like it is in this glass here, that water is actually bumping up on that penny. You can see that we have a nice little dome on that penny. Now, this is a fun experiment that you can also do if you do that dome on a piece of glass, on a flat piece of glass. You can actually use that as a magnifier, or as we will do in a future episode, we can use a drop of water as a magnifier to see all of the little critters that are inside of that water. But we have about 20 there now, and so I'm going to keep going. And I'm going to try and go kind of slow there. But you can see that that dome is actually huge. It's actually about 3 times the width of that penny. And what's happening there is that surface tension is actually holding that water together. The surface of a liquid actually has a tighter bond than the water underneath. So that surface is bound together. Now I'm going to, just as I said, kind of for sake of time, now you can see when I bump the table that little blue, that thing wiggles a little bit. Blue is a scientific term, meaning it's not a real word. So we are going to bloop, bloop, and bloop. Bloop is a scientific measurement of 1 droplet of water. As you can see now, we're getting pretty close here. You can see that water bouncing as we're adding that water, and it is continuing to get thick. Oh, there we go. So I lost track. But we had well over probably 25, 30 droplets on there, and those were pretty big drops, okay? So when you're doing this here, the students will normally just assume that that water is going to cover the penny and lay nice and flat, because that's how we normally see water. But this one is a discrepant event because it acts differently than we think it would. This is a very inexpensive one that you can do with an entire classroom, or you can do just at home with your parents and your grandparents, and you can show your brother that you're a little bit smarter than they are, and that you can get more drops on there than your brother. I have to take every opportunity I can to show my brother I'm smarter than him, because he's so much smarter than I am. But so this one here, this discrepant event is just droplets on a penny, and we're showing the science of surface tension. Okay. Now, as I said, if you wanted to kind of demonstrate a little further, you can go to some other types of coins. You can say, well, does the head side of the coin hold more water than the tails? There's a lot of fun things that you can do as far as experimenting with this one with variables. So if you have a science fair coming up, because I know it is science fair season, some of these variables would be a great way to test and to come up with a hypothesis of what and why and all those things. Okay, so that's a very small discrepant event. Okay, we are going to kind of size it up just a little bit here, not too much yet. We'll get pretty big toward the end there. But we're going to size it up just a little bit with balloons. Okay? This is another one that you can do at home very easily. As I said, I just grabbed a piece of tubing, really anything that is going to hold your balloons together, because what we want is we want the air to be able to transfer between our two balloons. Okay? So the air needs to be able to transfer between them. Now, what our question is going to be, or what our problem with our balloons is, I'm going to blow one balloon up with one breath. Okay? Now, if you've ever been to any of my classes, you know that I will ask what is actually in the balloon, and my answer will be Stinky Dave breath. Yes, we're going to fill this with Stinky Dave breath, so I'm going to blow up one balloon with one breath, okay? Now, one breath is approximately 1 liter of air, okay? Just kind of a fun fact. So we have our balloon here with about 1 liter of air. Now, I twisted it to hold it there, and I'm going to blow up the other balloon, and then I'm going to put it on the other side. Now, this one, I'm actually going to do 3 breaths, okay? We're going to try and do the same size breath for all of them. 1, 2, 3, okay? Now, these balloons are twisted, okay? So when I put them on my little tube here, unless I lose some of the air out of the, there you go. Right, I'm going to try this one again. There you go. So I'm going to twist it a little tighter there. When I put this on here, okay, our air is going to be able to transfer between the two balloons, okay? Now the question or the problem is, when I allow this air to transfer, what's going to happen, okay? Now, my logic would say they're going to equal out, right? We have one that's larger, we have one that's smaller. They should equal out, okay? But there's a couple different things that can happen. They can equal out. Nothing can happen because they've got equal pressure. One can get smaller. There's a lot of different things that can happen. So we're going to go ahead and untwist this one, so the air is now in there. I'm going to untwist the pink one, and we're going to see what happens, okay? So we have a small balloon and a large balloon, and we're going to see if they just level out or what happens with those balloons. Okay, so what we're seeing here is not too much is happening, even though our pressure on the small one and the large one, there should be a lot more pressure happening over here. If you look, we're actually even losing pressure on this small one instead of the large one. It's actually transferring the air from this small one into the large one. And the reason that that's happening is this small one, if you noticed, when I blew that balloon up, now if we took more time, it would continue to finish transferring over to this balloon, and this balloon would fill, and this one would be empty. We can see that this one is already shrinking up, and so what's happening here is our balloons are actually, that first breath made the most change, right? You'll notice I'm going to just kind of set this to the side and hope they don't go and fly all over the place. There you go. So we can see that small one shrinking into the large one. Now I want you to pay attention to what is happening here when I blow this balloon up. Now my first breath, you see there was a lot of change from here to here, right? Now watch how much change we have from my second breath. Not as much change. So what happened is the surface area has not changed much from that initial expansion. So when we do that, this little one here is actually able to transfer that over there because there hasn't been as much pressure on this one, okay? So we're going to set this guy to the side. As I said, you can see that it's already transferring that air over there. It would continue. It's a fun one to kind of watch as that's happening. But this one is transferring the air to the larger one, even though that's kind of contrary to what you would think, okay? So I'm going to set this one over to the side, and we're going to look at our next discrepant event. Now this one is a fun one. These are called, no really, these are called happy and sad balls, okay? So I'm going to let that one land. Now, we have two different materials here, okay? And what's fun about these is one of these is neoprene, and one of these is polynorbornene, okay? Polynorbornene, okay? So that's a weird word. Try and say that one 10 times fast. I can hardly say it once slowly. So we have two different balls here. I put this white paper towel on here just so you can see the balls a little bit better as they're landing. But we have a difference here. This is a fun one. This is a very inexpensive one. If you do want to pick this up, you know, you would have to go on the internet for this one here, but they're called happy and sad balls. And this is a great one for showing a lot of different physics properties, but today we're just going to kind of show one main one, okay? So the difference with these is I think this was the neoprene, and that's what's fun about it, is trying to remember which is which. So this one here bounces nothing. This one is dead, okay? Now, so this is actually my polynorbornene, and what happens is it's got a strange amount of elasticity, okay? And so when I drop this guy, nothing. Now, a normal ball, this bounces just like you would expect it to bounce, okay? This bounces like a bouncy ball. This is a neoprene ball. A lot of your super balls are made out of a neoprene-like substance, but this is actually neoprene. And so we get a nice little bounce out of this ball here, okay? As you would expect. Now this one though, when we drop them both together, you can see that there is a huge difference, even though they look the same, enough that it tricked me. So this little ball here, called our sad ball, it does not have that happy little bounce to it. I have another one just in case that one flew away. Now, wait, let me make sure this is the right one. Okay, yeah, this is my bouncy one. I do have another one of these ones. Now, the reason this is a discrepant event is normally you get a ball, you're going to bounce it, it is going to bounce, okay? But what we're seeing with this one here is because of the type of material in here. Now, when I was first researching these, I assumed it was like a dead blow hammer, okay? I don't know if you know anything about a dead blow hammer, but a dead blow hammer actually has usually pellets inside of the hammer. And so the inertia will continue those pellets moving, and then when it hits, the pellets will stop it. It's called a dead blow hammer because when you, wait, make sure these are the right ones. When it hits something, it just stops, okay? And so the reason you want that kind of energy is that when it hits, the entire impact is there instead of a hammer made out of just steel that will bounce, okay? So there's a lot of physics you can get into this one. If you've ever used a dead blow hammer, the first thing you thought the first time you used it was, I never want to hit my hand with this. After you've hit your hand with a dead blow hammer, you never want to do that again. I've learned that one from experience. But so what we're seeing here is you can say that this is just like your normal everyday hammer, and a lot of that energy is transferred back into bouncing that hammer up. This one is like a dead blow hammer, and the energy is all forced down, okay? So we can see that that energy is actually moved into the table rather than to bouncing back, okay? So that's a fun little discrepant event. This, like I say, is probably not something you already have at home, but they're very inexpensive to pick up. If you look under like happy sad ball science experiment, okay, make sure you put science experiment on that one. All right, so our next one, as we can see, our little balloon has almost lost its air there. I'm going to go ahead and get these out of the way. I'm going to move this one a little bit for our next experiment. And actually, I'm going to set this one down here because I'm going to be using a lot of the table for this next one, okay? Now, this next one, these are called wind bags, okay? Now, that's not referring to me because I am full of hot air. You just saw all of that nice little happy, sad balloons. But this is a wind bag. So it's basically a giant balloon, okay? Now, you saw when I was blowing up those balloons how one breath is normally 1 liter of air. This bag right here would take a lot of liters of air, okay? So what I'm going to do is right now it's actually a tube. If I were to blow into it, it would just shoot right out the other end. So I'm going to fill up I'm going to tie off this end of the tube. I'm going to come over here, and I am going to blow up this balloon, okay? Now, the discrepant event part of this is pretty fun. Again, this is not something you may have, but it is something you can purchase very cheaply or inexpensively. And so I am going to blow up this balloon. Now, we saw how big our balloon here got with 3 breaths, 3 liters of air. I'm going to see if I can fill this entire thing with Stinky Dave breath. Okay, are you ready? Now, I'm only going to go to 10 breaths, and then we'll stop, okay? So what's fun with this is we can make a guess as to how far I'm going to get with 10 breaths. Having done this before, I'm going to say I'll probably get to about right there with 10 breaths, okay? So here we go. And if I pass out and I fall behind the table, just give me a sec. I'll get back up and act like it never happened. Okay, here we go. Ready? Whew. Whew. Okay. So I got about, I was pretty close on my guesstimate there. I got woo-hoo-hoo-hoo. I'm a little dizzy there. We saw that I got about this far when I was blowing the air into this thing, okay? So you say, well, where's the discrepant event in that there? Well, I wasn't really using the power of science, okay? This one here is the Bernoulli effect, okay? The Bernoulli effect is in use a lot with a lot of different things, making airplanes fly. When firefighters are putting out a fire, you will sometimes see them shooting water away from a window instead of into the house, and the same thing happens here. The Bernoulli effect is that fast-moving air has a low area of pressure, okay? And so the pressure around it is a low area of pressure, meaning it's a vacuum, okay? So instead of me putting my mouth on here and just filling this with Stinky Dave breath, I'm going to do it a little bit differently this time. And contrary to what your brain might say, I'm actually going to hold my mouth away from the balloon, okay? And we're going to see how far I can get in 3 breaths by holding my mouth away from the balloon, okay? So here we go. Ready? I got to breathe. I've been talking a lot. All right, here we go. 1, 2, 3. Oh, now in 3 breaths, I was actually able to just about fill this thing up, okay? So what happened here is that Bernoulli effect, that area of low pressure actually created a vacuum and sucked a lot more air around from around it. Instead of this just being Stinky Dave breath, this is air from all around, okay? So what we saw there, an easy way you can demonstrate this with students is if you take your hand, okay, and you blow on your hand, okay? Now what you're going to notice when you blow on your hand, like this, like you're going to whistle or you're going to blow out a candle, you're going to notice that that air feels cool, okay? Now, that's because we're using the Bernoulli effect. We're actually sucking in the cool air from around our face, and it is sucking that toward our hand. So we actually have a vacuum there. Now, if you want to change it to where it is more of your stinky breath, or in my case, Stinky Dave breath, you're going to bring your hand a little bit closer, and instead of going like you're going to blow out a candle, go. And as gross as that is, you can feel the warm air from your lungs. Now, no, but what happened there is this way we don't have that nice cool air that's being sucked in because of the Bernoulli effect. Now, the Bernoulli effect helps airplanes to fly, right? We have the areas of low pressure, the areas of high pressure. It helps in a crazy discrepant event like this where it's sucking things into it, as well as, like I said, even firefighters. So these things here today are all what are called discrepant events, and that is when science does not work the way you would picture it, okay? Your brain says, yeah, you can't hold your face far from a balloon and blow it up. because you're not getting any air in there. Or like our little happy sad balls, a ball is going to bounce. Well, it doesn't always bounce. So these little things that we're doing here are fun. The ones that you can do in a classroom or with your students very easily or do at home are this nice penny one here. If you have a science fair coming up, I keep mentioning a science fair because I have a big science fair coming up. But if you have a science fair coming up, this is a great experiment for that. Our balloons are a great experiment for a science fair. If you've got just very little bit of cash, you can find these other ones online. Okay, so I am Mr. Dave. I really appreciate you guys for watching. Thank you for joining us for the RayKitty Science Project. And as I end all of my shows, don't forget that science shows you matter.